Now that we have covered electron configuration, I want to show you how you can use the electron configurations to determine the magnetic properties of an atom. So we divide the magnetic properties into two. Paramagnetism, which means that a substance can be temporarily magnetic. That's when it's exposed to another magnetic substance. Or diamagnetism, okay, so no magnetic properties. So paramagnetism results from at least one unpaired electron. So you have to write out the electron configurations and actually the orbital diagrams. So practicing this will give you practice with everything really that we've covered so far in these units. So it's a real good thing to practice. So you may know from physics that magnetic fields come from any charged particle that spins. And electrons are charged particles and they are spinning, and so they emit a magnetic field. Now, if we have an orbital, and you know, the conventional symbolism for orbitals is the box, although sometimes you'll see them as circles, and electrons are typically represented as the half arrows. This meaning spin up, this meaning spin down. So if you have an orbital that is full, the magnetic fields emitted by both of them cancel out, okay, because they're spinning in opposite directions. So it's like wave interference, okay? If you have an orbital, on the other hand, that only has one electron in it, that is going to emit a magnetic field, which is going to be attracted to something else that's magnetic, okay? And so what we're looking for is to draw the orbital diagram / electron configuration and see if we have any unpaired electrons. And you really do have to draw out the orbital diagram because you remember from Hund's rule, you get to equal energy multiple orbitals like the p sublevel, d sublevel. Hund's rule says that put one electron in each empty orbital before you start pairing any. So let's look at some examples. Let's say I asked you a question, is sodium diamagnetic or paramagnetic? Prove it. Well, you would first have to draw out the electron configuration for sodium. Let's do shorthands now that we know how to do that. And then what you want to look to for paramagnetism or diamagnetism is just the valence electrons, just the last electrons to go in, okay? Those are the ones that really have a chance of being unpaired. So we know that the S sublevel only has one electron, and this exponent tells us, S sublevel only has one orbital, and we know this exponent of 1 means there's only one electron in that orbital. So yes, in fact, sodium is paramagnetic. Let's look at a couple more of them. Magnesium, on the other hand, its highest energy or valence electrons, 3s2. So the 3s orbital, and again, you can draw it with a square or a line or a circle. Okay, either one, any of those are perfectly fine. But you can see that the valence electrons are paired in magnesium. So magnesium is diamagnetic, would not show any attraction to something else that's to a magnet. Now, the more unpaired electrons you have, the stronger the attraction that substance will have for a magnet. And so we're going to look at the effect of paramagnetic things, like how you can tell in the laboratory that something's paramagnetic. It turns out that if you have unpaired electrons, if you have a paramagnetic substance, it is going to appear heavier using electronic balance because it's going to be attracted to the magnet in the electronic balance. So paramagnetic substances, again, will appear heavier in a balance. It's pretty cool. There's some labs like that. I'm going to take just a minute and talk about transition metals because they are most frequently paramagnetic. And that's because in a D sublevel, there are 5 orbitals. And of course, following Hund's rule that you put one electron in each of these equal energy orbitals before you pair any of them, you can see there is lots of opportunity in these D sublevels to have paramagnetic substances. And you can have as many as 5 unpaired electrons, which makes it strongly attracted to a magnet. So let's see. I also want to remind you that often the real common paramagnetic substances are ionic compounds containing a transition metal. So let's say that we had iron 3 chloride and that I asked you, hey, is that paramagnetic? Well, you would have to look at each of the substances that make up iron chloride. And this is not neutral iron, right? This is iron plus 3. So you have to know how to write out electron configurations for cations and anions. So hopefully you remember that when you're making a cation of a transition metal, the electrons in the 4s sublevel get removed first. So if I were making iron plus 3, I would remove those first. And then and only then can I start to remove electrons in the D sublevel. All right, so iron plus 3 has 5 unpaired electrons. So it's quite paramagnetic. And that is it. Just a brief little discussion of paramagnetism versus diamagnetism. There is a practice worksheet posted in D2L for you.